It's as simple as this. Okay, and then the Q here is K minus K prime. The way I put it here in this. So this, and if you work out Q square, Q square is K minus P K prime whole square. I am doing this kinematics because it's very important that we understand the kinematics of the process before we do anything with it actually. Okay, so this is simply just take a dot product, and you will find that the dot product is just if we neglect masses, it will be K dot K prime, which will be EE minus again E prime the angle between them. So it will be 1 minus cos theta. You write it as a sin square theta by 2 or something like that. 2 sin square theta by 2. So this is as quite simple. And then when I said W square is actually Px square. So for this particular kinematics, it will be K plus P minus K prime whole square. Okay, which is simply P minus Q. I am just using this, this energy momentum conservation. Okay, so P minus Q whole square, just simply performing little algebra, you can show that it is Q square plus M square minus 2M into E minus E prime. Q is actually, because I am working in center of mass frame, so you have a very simple situation where any dot product with this 0 will be 0. So dot product with P is always proportional to mass and the energy component of what you are dotting with actually. So so simple, and this just tells you that the bound on this W square. So W square is always greater than this it's lesser than this number Q square plus M square by this amount actually. This is positive, this is positive, this is positive, this is positive. So it just tells you the range of W square. Okay, and lowest value that this can get is actually this is just the proton mass actually. Okay, so that's how it is done, proton mass plus Q square, because there is energy coming in, proton will have some energy, and together this determines W square. That's invariant mass that you produce. It is like in a collision, you look at final states, you can ask the question, what is the total mass that is produced or energy that is produced? That is what is denoted by the W square. Okay, so that's about this. And of course the center of mass energy is always greater than or equal to this M square, because you can see this K dot P will add something to it, so it will be always greater than M square. So these are certain things that you should keep in mind. I also have a very short notation, so I have too many notations, so let me just not. Okay, so I can define something called nu, which is P dot Q by M. Again you can see nu is just the energy, like sort of carried away by this photon, the intermediate photon, because if you work in center of mass, rest frame of the proton, this will be M times E minus E prime. So that is the difference in energy that goes into this system. Okay, so this is all about this kinematics. Okay, what we are interested is the cross section for this process to take place. Cross section is just an probability. Okay, probability where you see a final state with an electron having a definite K prime and a set of a bunch of hadrons in the final state whose total invariant mass is W square. That's what is called observable. Okay, an inclusive observable means you sum up or sum over all the final states except the lepton. In this case you sum over all of them. So the sigma, when I say sigma inclusive, it's called inclusive. Those who are hearing it for the first time, inclusive means you sum all the final state, okay, which includes everything. It could be leptons produced in this reaction. You might wonder how proton can produce lepton. It can produce because electromagnetically, it can produce photons. Photons can pair produce leptons. It's all possible. So this px can contain everything, that is possible in any scattering reactions that is allowed by these three interactions, particularly electroweak and strong and electromagnetic. So all that. Okay, so this is a inclusive process. So you sum all the final states. Okay, I mean you still call inclusive if you keep lepton momentum fixed or energy fixed in your. Basically, you put your detector somewhere here, and then you look for events that registers on it with a specific energy and momentum. Okay, and you don't care about whether elephant is produced or electron is produced. That's all summed up actually. So you just include everything that is that is produced in these reactions. That's called inclusive process. Okay, so that's the meaning of this. Okay, so now if I want to calculate the sigma, I need to do this following exercise. I have to square this amplitude, and like yesterday I mentioned, when you square this amplitude, you have this factorization, very simple factorization of leptonic part and hadronic part. Basically, the square of this the top portion will separate out nicely from the lower part of the diagram actually. So the upper part of the diagram, which will be this times this symbol doesn't mean anything, it just says product amplitude. This part, because this is a k, this is k prime, this is k prime, this is k, this amplitude, there is a vertex mu here, there is a vertex nu here, this is called leptonic tensor. So L mu nu, it will be a function of k and k prime, you can always write it as k comma q. And then the lower part of the diagram, okay, again if you just look at this, okay, this is proton, this is proton, this is px, this is px, just a squaring, it's not an integral. So just multiply, this is the complex conjugate of this, I call it as W mu nu. W mu nu will be function of P comma Q. So the only momentum that is common to these two parts of the diagram is Q. The Q is the one that connects the lower part of the cross section and the upper part of the diagram, the leptonic and
I mean, in which part do you consider it?
I am just writing down the individual parts. I will write down when I write the cross section the intermediate part.
So it is not included in either of
them actually. Yeah. So if you write the the cross section sigma or d sigma, whatever you like, actually it will be 4 times k dot p. For those who are not doing particle physics course, this is 4 dot k is just the flux of the incoming particles, lepton and the proton, and you have a 2 times 2, which is actually because you have 2 spin-off particles colliding, you need to average the spins off times off, and as I said, sum over all the final states, and integral, let's call this is x, okay, the momentum of k prime 0, that's the phase space for this the electron that is coming out, and this is the total this is the energy momentum tensor times we need the matrix element for this particular process, okay, times this. So this is the amplitude for the process, and this is sum over all the final state. This symbol denotes you sum up all the final states produced in this reaction, and this is I have separated the leptonic part from the remaining parts actually. So these are the two summations that you require to do. Is this sigma x I mentioned in the previous talk, that sigma x is just the product of phase space of this kind with summation. So all possible final states 1, 2, 3, 4, etc. And for each of them you will have this phase space vector like this actually. Okay, and this px denotes is sum of all the momenta of the final state particles that are produced in this part of the diagram actually. So this is as simple as this results from field theory. So now we look at how the matrix element looks like. How far we can write down actually, even though we don't know the internal structure of the proton, just using simple electromagnetic structure of this proton, we can actually write down at least how the interaction looks like or the transition amplitude looks like. So this is u of k. I'm dropping all the spins. If you want, you can put it this small s prime, small s, and stuff like that. And then when you do this summation, okay, I need to be taking care of all the polarizations. Usually you sum all the final states, momentum, and spin, or any quantum number that you can associate with the final state. You need to sum. You need to sum because in an experiment we don't really pay attention to those things. We just include both up spin, down spin, blue color, red color, everything that we include in the final state. Hence this summation is done in any theoretical computations. Of course you can also do without summations. So this is 1 by q square. This is the q square that you was asking. Okay, this is the momentum transferred square that corresponds to the propagator, and then this is minus c times, I am writing down electromagnetic current for this for this block, this reaction actually. The P goes to Px. I parameterize by a symbol. I don't know how it looks like, whether it looks like a simple function like this or more complicated than this actually. I have no idea, but I just all my ignorance I just put it here. Yeah.
That should be there, no?
That's what I said actually. Phase space for the final state particles except the lepton, all sort of put it in this sigma x. Sigma x means
even the integral also.
It's all integrals actually. This is just a symbol. The symbol x means, if you want, I can write it down. It is more like you take any possible pi. Let's say p prime to p prime 0. This is the phase space of one particle in the final state. Now if you have n particles, so you will have n such things. You sum all possible n's. You can have 1, 2, 3, 4, etc. So you just do this. It's a kind of summation that you do always, no? So I want to sort of spend more time on this because I'll show that this is irrelevant because I'm calculating an inclusive process where this information about the final states will be sort of washed away if I do little algebra. You'll see that actually why that's irrelevant actually. Okay, so
is this form the only possible form for this matrix element?
This is, you are asking whether this is the only form or? Yeah. So like yesterday I mentioned that if you allow only single photon exchange for a process of this kind, then and assume that photon interacts with the proton, because proton being charged particle, okay, the interaction is electromagnetic, and this is the only term. And if you include 2 photon exchange, 3 photon exchange, then you will have more and more terms actually. So I make an assumption that I consider single photon exchange. Okay. Yeah, that is fine. Okay, so what is W mu? So I'll have to just see by substituting this, in this expression, and I should be able to show that this entire cross section can be written in terms of L mu nu and W mu nu. It's very simple. Now if you look at it, you just put this expression, square it. When you square it, this part, the square of this will be square of this, modulus of this, and the square of this. So it's, nicely separates out, except that there is an index which connects these two parts. Okay, so that is all. So it's a simple exercise. You just substitute, and then write it in 2 parts. Okay, and I'll just write down how the final expression would look like. So I'll just look at d sigma by d cube k prime. I just bring that d cube k prime to this side, and k naught prime also to this side, leaving out all this factor 2, etc. This will be simply k dot p, which is flux alpha by q square whole square L mu nu. This will be k comma q times W mu nu p comma q. So the q is the only thing that connects apart from these 2 indices that connect. Okay, you can see this is leptonic and hadronic. The leptonic part I'll just write it down here for the lack of space. So L mu nu will be just square of this, take this and the complex conjugate, basically this quantity, u bar gamma mu u bar gamma nu u. I've left out all the arguments. It's called L mu nu in short. Okay, maybe I should put some over. Yeah. Just a minute. SS prime. Then 1 by 2, 1 by 4. I don't know why I put 1 by 4. So it's, yeah, tell me.
So the argument of J mu is 0. So is that in the position space or momentum? Because why is it 0? Why isn't it like J mu q square as it was in last time you defined form factors? It was like J mu tilde q
that,
square.
Yeah, it was actually, no, that was, this is, you are talking about why this amplitude is independent, at 0 position, is it? Right. It is 0 because if you really work out, the transition amplitude, okay, it will be all integrated, that x dependency, and it will be there in this delta function actually. So because if there is an x dependency, that was actually using this translation invariance, because when you write down an amplitude, you will have an, you do it in position space. You will have an integral over, positions, and if you pull out this x dependency from the currents and integrate this, this position, you will get this delta function. This delta function results from, currents. This current is also now, written in the momentum space. So there will be, this kind of, j of x for. For this part, this is like, you have a x and y 2 positions in position space, and if you calculate, currents in x space and then do the x integrations and y integrations, because you are calculating everything in momentum space, then this x dependency will translate to these 2 momenta, and then this y dependency will translate to the px and k, px and p prime. So this.
I would have thought that we do a Fourier transform and all j of x becomes j of some q's p or something.
This what is not done. This Fourier transformation is not yet done actually here. The position space, current is kept as it is here actually. So that's how it. Yeah. Okay. So basically, if you recall, I would have to go back to this. It is like, you have 2 current J mu of x and J mu of x. If you call mu and nu, okay, this is a mu and this is a nu. Okay, this is your, second order contribution coming from your interaction term. This is like a hi times hi. Okay, and each hi is an integral. Okay, because d4x, and from this you only calculate this transition matrix element. When you do this, perform this integral over x and x prime here, x part actually will translate to this pk, and then remaining x prime part will translate to this actually. Until now there is no Fourier transformation. Okay. Okay. So maybe we can work it out actually during this afternoon sessions. I can show you how it comes about. Okay. So, and what about W mu? So this part, leptonic part, is trivial and it is calculable, because we know this U's and U bars, and manipulation with U's and U bars are very straightforward, so you can perform this. What about W mu? So W mu is this what you call hadronic tensor. Okay, and this I'm not making any simplification. I'm just writing down what I get, unlike in the previous case. So it is 4, okay, px minus p minus q. I'll explain to you this why I'm putting this. So off times sum over spin of the proton. This is ps, j mu of 0. This is x times x ps. Okay, and again this s is actually is spin of the proton, because I'm considering as experiment where I don't care about spins of the incoming or outgoing. That means I average incoming spins and sum all the final state polarizations. And this just tells you that the answer that you get will be independent of a specific spin configuration. This is the same delta function that I have written down earlier, and this same delta function. So this is just W mu. So just this part, this is the complex conjugate. When I did the complex conjugate, current being real, emission, so you don't need to worry about putting dagger and things like that. So it's just J mu. Okay, so this is sum over x, correct. So note that this summation at this stage is quite non-trivial, because there is x hanging around. Unless I know what j acting on x look like, I won't be able to do this summation actually. Okay, so I kept as it is x, and this x, this this px is sort of appearing in this expression. So my next task is actually to really see how I can get rid of this x, because I want a W mu which is sort of independent of what final state that I produce actually. Because if I have some px hanging around, then I should know the complete information about what are the particles that I produced. You collide an electron and proton, you produce all kinds of stuff actually. I want to sum them up. Experimentally it's easy to do it actually. Yeah. P of this is minus actually. Yeah. Sorry. It's just the same delta function that I have written down here. Here this k minus k prime is q. If you just use this kind of, I've just in short I have written down, because W mu I don't want to write k and k prime. There's only one q which captures this k minus k prime. Electromagnetic current, I assume that this. Is that okay? So if I do detail, then there will be a lot of questions, of course. I don't mind if you ask questions. Please do ask if there are some questions. Okay. So now I want to sort of get rid of this x. Okay. Then I will have a simple looking expressions, because if I really have the x, I won't be able to calculate anything. And experimentalists are smarter because they sum all the final states. They don't have any information about final state. But as a theorist, I see some something that is needed. So how do I get rid of this? Actually, the way to get rid of this is actually just use translational invariance. Means I want to sort of use this translational invariance. Namely, if you can always relate j at different space-time points using this IP operator x times j mu of 0 e power minus I p at of x. This x is a position. You can call it as I also if you are not confused with this. Okay. So all I'm going to do is actually I just replace j mu of 0, for example, by this. If I do this, then I can show that this px can be completely taken care of. How? Just replace this p as I'll show you some small. If I write it as minus I p at of x j mu of 0, sorry, j mu of x, okay, e power I p at of x this part, this will give me e power minus I p dot x, and this will give me e power I p x dot x. Okay, and I can write down this exponential delta 4 of px minus p minus q in such a way, that means I can write it as d4x by 2 pi whole power 4. Okay. E power minus I px minus p minus q dot x. Okay, and then this is okay. I can write down my delta function in this particular fashion, where px is here. Okay, and then I manipulate this with this, and then try to show that all these p is this capital P small p and px cancels with this, and you'll be only left over with e power plus iq dot x times this quantity. Okay, so somehow this you can get rid of px by just calculating this delta function along with this this translational invariance property. So if you do this, then you will see that mu is, let's write down actually what I get. It's easy. I'll just work out this part. So 2 pi is there, sum over x is there. 2 pi whole power 4 into delta function will be this integral d4x by 2 pi whole power 4 e power minus I. So it will become plus I q dot x, px, all p's cancel. Okay, then half of sum over s ps, okay, j mu of x. This x, capital X and small x are different. This is a position and this is j mu of 0 ps. So now you can see that this sum over x and this part can be set equal to 1, because the rest of the expressions have no x dependency, capital X dependency. So you can use this identity sum over x, which I said how it looks like if I express in terms of phase space of these final state particles. It is the sum of all possible phase space 1, 2, 3, 4. For each one we'll have a phase space integrals measures. If I use this, then I can completely get rid of this. Then you end up with an expression which is did I take care of this 2 pi whole power 4? Yeah. No, this is J mu x, yeah. X is position actually.
Yeah, with that, how can you do this like identity?
Like? I did,
How can you perform this identity?
yeah, I said no, this x and capital X are different. I said that. Probably I chose a wrong notation. This x is x. This is capital X. This is small x. Okay, you can put psi if you like it actually. So maybe I'll just if it confuses you, I can just write down. Is it okay? Yeah. So you get 1 by 2 pi integral d4 psi e power iq dot psi. Okay. You get half of these polarizations j mu of psi, j nu of 0, ps. Okay. So your W menu, which had this information about the final states, is now completely gone at the expense of introducing the argument for this electromagnetic current J. Okay, so you get for W menu Fourier transformation of product of two electromagnetic currents at two different space-time points sandwiched between proton states with specific spin, and the spin is summed over actually. So I forgot to put this S. Okay, so everywhere it should be there. Yeah.
So is it right to say that so there is some sort of cancellation happened between two terms? Is that correct? So while the first term manifestly has a P capital X dependence, I can't really see it in the second term.
In the second term is?
In the J mu term. The
J mu.
Yeah.
I can put anywhere I like actually this, this e power, because all I did was actually I introduced this quantity. I could have introduced here also if I like.
That's true.
But that will give you something unphysical actually.
He's talking about the state X,
X, yeah.
not having a momentum level. Yesterday you had.
You want a momentum level, is it? Is that what you wanted?
That right.
This is actually X actually means, a state of n particles, n can be some fixed number, with the, individual momentum could be anything, but the total momentum is capital Px. So that is how you should understand actually. Okay. So this state is basically nothing but this collection of n particles, okay, and n could be arbitrary, and I am actually summing all possible n's. N could be 1, 2, 3, 4. If it is a one particle, the phase space is actually this. If it is two particles, it will be product of two such things. Three particles mean this, and then I consider all possible such final states and sum them. And we know that that such a sum that I explained is 1 identically. If I have nothing else, if there is something sitting in front of it, then it is no longer 1. So I have exploited this fact by by just cancelling this Px dependency at the expense of introducing Xi dependency here. Okay, that's how it goes, and it is as expected. I'm in an experiment, when you calculate these inclusive cross sections, the experimentalist won't have any information about the final state because he sums all of them actually. In a summation, everything it gets wiped up. Whether it is a spin of particles or spin 1, or it is hadron or lepton, all in such informations are wiped out, and that's what I get in my theoretical expressions also. I don't have any information about the final state. Yeah.
Earlier you said you are excluding some leptonic states, right?
But I am still doing that. I kept leptonic part here. Here, but it sums everything. If there is elephant produced, that's also summed actually.
There all the states are
Everything actually. Everything that, even if I don't have anything in it's a sensible theory, If it is produced, it will be wiped out. Okay, so that's called inclusive. Okay. Okay, this is a better expression compared to the expression that I have here, because I'll show you, how to proceed with these expressions, because it contains no information about the final state particles. So that is something that I wanted to emphasize here. Now let's move on and see what we can do. So as far as this cross section is concerned, the half of the expression is already known. The second half is written here. That has a nice looking structure. Okay. Okay, as you can see, it's only function of p comma q. P is the momentum of the incoming proton, q is the momentum that is transferred in the scattering reaction. So it's just a Fourier transformation. If somebody gives me the form of the current, I can do it in 5 minutes what the matrix element would look like, and then calculate the Fourier transformation. I have an answer for these things. If I just substitute as an exercise, you can try. If you have if J mu is proton is an electron, and substitute electron current J mu J nu, evaluate the matrix element because it's straightforward to evaluate, do the Fourier transformation, you will get an expression which is very similar to this, almost identical. Okay, only p the argument of this u's and u bars will be replaced by p and p prime. That's all. So it's as straightforward as this. But unfortunately for proton, we don't know what J mu is, except that it's an electromagnetic current. We don't know the form, but we have an expression to deal with actually. So how do you deal with this actually? So let me just proceed and see how this can be studied further. To do this, okay, so I'll have to say a few things about this experiment. This process was studied in I don't know, in 60s, 50s and 60s by people like Callan, Jacques, Gross, and Bjorken. Bjorken is one of those. Gell-Mann. There are many people actually. The famous field theorist. This was the first process people studied because it deals with some object which people have never understood that time. So that was the reason. And expressions like this were really challenging to them actually. So they wanted to look at without introducing any model for proton. They want to study this just as a mathematical object. Okay, so to do that, people had to do little more with this. That was the following. You can show that the following is true. That is, if you take d4 psi e power iq dot x psi, sorry. Okay, and again this sum over s ps j nu of 0 j mu of psi ps, you take this combination, which is big j's are operators. So if you take this combination, j nu is 0, g nu is 0, j mu is just the reversed version. Calculate this matrix element using similar approach. Just go back and see what would be this expression, corresponding expression, and you can show that the delta function that you will get, okay, will have a wrong px minus px. Okay, if you have a wrong sign for the px, then that process is not allowed actually, because it will give you some. That's an exercise. Maybe you can try it actually. Okay, so this is not allowed kinematically. Okay, you can try this actually, because if I just start with this, introduce x and use translation invariance and go back and write down this expression, you will find an amplitude square which contradicts with your initial kinematic constraints. Okay, that is an exercise. It's very easy to show.
Amount to just flipping q to minus q.
Flipping minus 2, yeah, you can do that also by just flipping minus q to minus q, and show that actually that it gives you the wrong kinematic configuration. Okay, it won't be a deep inelastic scattering if you just consider deep inelastic scattering. So this will be identically 0 for a deep inelastic scattering kinematics. Hence you can write W mu nu just using this. I'm just subtracting this 0 from here, so I'll get 2 pi integral d4 psi e power I q dot psi. I'll write a shorter notation for I drop S completely, assume that this matrix element is computed with spin sum, okay, spin average rather, and this is a commutator of 2 electromagnetic currents. Okay, people tried to write down this because in 50s and 60s when there was no field theory for or quantum field theory for strong interaction, they used what is called current algebra, meaning you know what algebra is actually in group theory language. If you assume these currents are certain representations of group, then they actually they transform like vectors, and then and you can actually impose certain commutation relations among them. Okay, these currents, and there is a very nice literature on this current algebra. So this current algebra is just using some group theory ideas and imposing certain commutation relations of these currents. Basically, if you assume that this current satisfy certain algebraic group theory algebra, you can relate this product of commutator of currents to some simpler objects, and then those simpler objects, matrix element of those simpler objects can be parameterized in terms of some simple functions, and study this without really knowing the form of the currents actually. Okay, so that in field theory that if you have two charges at different space-time points, and you can actually write down a commutation relation. For example, if you have a SUN group, okay, you can write currents something like this TA psi, and these currents the group theory tells you that the current satisfies certain algebra psi bar if it is x, this is 0, nu, tau b, psi 0. You can actually show that this commutator of these currents has certain group theory algebra, like a J mu A, J mu B will be proportional to some structure constant times J nu C or whatever. Okay, so you can show that because it simply follows from the group structure of this. Okay, similar thing was tried by assuming that these currents belong to certain symmetric group, and if you assume that such a algebraic structure, then you can write down as a product of currents as some coefficient times some another current, single current, and calculate this matrix element. This goes by the name current algebra. That means even if I don't know anything about dynamics, I can talk about how the currents satisfy certain algebra. Algebra means this commutator of these currents can be written in terms of currents themselves actually. Is this clear to roughly? Okay, you don't have to go into details because that's a huge literature, but it was a very successful approach prior to knowing the full theory of strong interaction physics. In fact, quite a lot of things were derived in strong interaction physics by just using this symmetry principles. It's clear. Maybe I'll give you some example in the afternoon if you want actually, which are very elementary. using some SU2 group you can you can construct currents, and then this current satisfy some algebra, okay, in field theory, meaning two currents can commutator of two currents can be written in terms of sum of single currents, okay. So that idea was used, and then people could actually make progress. That was the first thing, okay. In that context, people like Callan, Gross and Jacques and Bjorken studied these currents and derived some rules, okay. I will not tell you what those sum rules, because those are a topic by itself, but I will just just take few things, and then I will tell you there was some tremendous progress, and that led to what is called a scaling, and that was the beginning of strong interaction physics. This is an era of strong interaction physics, I would say, thanks to Bjorken. With this story apart, let us proceed with this. Okay, so I can take two routes. Maybe I will tell you what I wanted to do before I proceed. One is, I don't care about what Callan and Bjorken and all did. I'll just assume what is this particular form and proceed. That's one way. Proceed means the approach that I took yesterday. I had a single current sandwiched between P and P prime, and I parameterized in terms of momenta, substituted in my expression, and compared it with the experiment. This form factors. Okay, that's an approach that I took yesterday. I did not ask what Callan did and Jacques did. Okay, I can follow exactly the same step. I don't care what they did. I just take this expression, and like an undergraduate student, I will want to write down this product of two currents between proton states, in terms of some functions. Okay, and then proceed. Maybe I'll take that as a first step, and then later on I'll come back and study this the way Callan and Jacques and Gross studied, and show you some interesting properties. Okay, so these are two aspects of the same thing, but I'll show that both are leading to the same picture called Parton model or factorization. Okay, so I'll take the first approach, undergraduate student approach, namely I will proceed with this simple looking expression d4 psi, and express in terms of some unknown functions. As I said, I can't compute this quantity, neither commutator nor the matrix element. If I know how to compute commutator, at least that is a one progress. And even if you compute the commutator, you need to compute the matrix element of that commutator. That's also another non-trivial top. So I am not going to do any of these things. I will just use this tensorial decomposition, meaning noting that this is a rank 2 tensor, okay, and these are two electromagnetic currents. They are vectors. So the W mu nu is a rank 2 tensor, and because you can show that actually if you consider electromagnetic current, it will be symmetric in mu1 nu. Okay, even though it looks like antisymmetric, they don't it doesn't look like it is symmetric or antisymmetric, but you can show that if its J mu is symmetric, it will be a symmetric rank 2 tensor, and I want to express W mu nu in terms of symmetric rank 2 tensors. So what are the symmetric rank 2 tensors that you can construct from the structure of the right hand side? Yeah,
Which will vanish when you contract it.
yeah. Oh, that is another constraint. Yeah, I will come back to that actually. Yeah, that's correct. So, and that tensor should have certain properties. I will list what are the properties that tensor should satisfy.
This is the expression.
Yeah.
Saying that it has to be symmetric. This thing, if you commutator, exchange menu, that clearly is giving me minus sign.
The sign will be there, but you need to worry about the psi dependency. Again, use the translation invariance back. You can show that, and it is symmetric actually, provided this current is the electromagnetic current. You can show that.
You have to bring the psi on the first.
Exactly. Okay, so it is symmetric, rank 2, and there are additional properties like, because it's an electromagnetic current, this is true for any indices. Okay, so if you contract Q on it, it should vanish identically. Okay, so that means this is what Imani was mentioning, has to be 0. The other properties, this is electromagnetic current, so you should worry about the time reversal invariance. Parity, for example, it's electromagnetic current preserves parity, right? So parity means if you look at 0 I, under parity it should go to minus of 0 I, because parity changes all the position part, time part is in there. So all that you should take care of it actually. So this is, so I list parity, time reversal, symmetries. So I have quite a lot of things at hand to write down my W menu in terms of vectors that are available in the expression. So what are the vectors here? P and Q. Spin is summed over, so I don't need to worry about spin part. So only P and Q are available with me, and I will write down what are the possible tensors that I can write down. So there is a big list I can write. So P mu P nu, Q mu Q nu, and P mu Q nu plus P nu Q mu, comma, what else? G mu nu. That is the most simplest one. And I will not be able to write down terms like mu nu lambda sigma with P lambda Q sigma, because I am considering only the symmetric part. This may appear in some other context actually. If I am looking at instead of photon exchange, if I look at Z exchange or something like that, then you have a parity violation. That parity violation can introduce this kind of tensors. Okay, and you can also, suppose you have a process where time reversal is violated. Okay, you can have these antisymmetric parts also. So there's a lot of things that I can write down, but I will not consider all of them. I will consider only those which satisfy this condition: current conservation, parity, time reversal. These are the things. It has to be rank 2. Okay, you can do this. This is clear to everybody. So you can do this. Just putting some unknown constants A, B, C, D, and use these properties. Apply Q mu on this, Q nu on this. Write down set of equations. Solve for A, B, C, D. Okay, and I'll write down the answer. You can try it during your afternoon sessions. W menu takes a very simple form. What is that form? So yes, let me write down some the right one, otherwise I will have problems later on. So W1 can be written as minus G mu nu plus Q nu by Q square times W1. I'll leave this part plus okay. I drop other terms because those will not fulfill all these properties that I have written down here actually. So this is very straightforward actually. Anybody who knows how to do tensor decomposition vectors available in theory is, we will be able to construct this. And because it's a rank 2 tensor, I have already taken care of this rank 2 nature. The remaining, these unknown coefficients will be a function of invariance. The invariants are only p square, q square, and p dot q, right? So it will be p square, q square, p dot q. You can drop p square because it's just mass of the proton. It is not telling you anything big. So it's in principle it's a function of q square and p dot q. So I'll say this wi or wi of q square comma p dot q. Okay, this is an important point. Yeah. Why didn't I consider this? This one. This is antisymmetric in mu. This can appear only when the currents are weak currents. For example, if you have gamma phi axial currents, this is a vector current, so you cannot have such. Very good. So I'll skip some steps. Okay, all you need to do is actually you take this W. Now we have some structure for W. It is much more easier to handle than the previous ones with complicated Fourier transformation, etc., etc. You can use this like we did in the last class. We parameterize current in the last class. We did not calculate parameterize the square of the current. Current itself we parameterized. That's the difference. Here we are parameterizing the product of two currents sandwiched between proton states. That's what we are parameterizing. There is a difference between what we did last time and what we do now actually. Okay, so that point we should keep in mind. And in the literature, these W's are called structure functions. Okay, now you can plug in this expression in your original formula that I had written down in this part of the board and calculate the cross section. And the cross section will have everything known except these two structure functions. So I'll have an expression, unlike in the previous case with a lot of summation, delta function and stuff like that, you will have a very simple looking expressions and containing only these two unknowns W1 and W2. That's good news, because even if I don't know what they are actually, you can get some numbers for it from experiments. Okay, I don't have a theory, so I cannot compute them. Okay, let me accept my whatever inability to compute, but at least you can get what from experiments what this how these functions look like as a function of q square and p dot q. That will give you some idea about this underlying physics of these currents. That's the goal of us, no? Because theoretically you cannot actually write down what J mu. Whatever symmetries that you use, you cannot write down. These matrix elements cannot be computable actually in a theory unless you have a super theory. Okay, this point, this is the only thing that you can get, and of course you will see this a lot to learn from the data on these structure functions. Okay, these structure functions. Okay, now you substitute this. That's straightforward. I will not spend too much time on this. So you calculate, like yesterday I was calculating, the distribution of leptons, both in solid angle as well as in energy. Okay, is very similar looking formula. Okay, if you see, I'll show you the comparison actually. Q power 4. Okay, P dot Q. Let me just use some standard notations. Plus W1 P dot Q Q square sine square theta by 2 . So you'll have a part which, let me just write down whether I've written it correctly. There's a 2 times sine square theta 2. So theta is the this scattering angle. If you do a scattering experiment, okay, if it is lepton, this angle is theta. So it has a solid angle d omega, and the energy of this is actually E prime. Okay, rest of them I have integrated out. So I think I have written down what capital Q square was. Q square is minus Q square. Minus, why I put capital Q square is minus Q square, because minus Q square is minus 4 E prime sine square theta by 2. If you go back to your notes, the first page, here I had written down this expression, and minus Q square is positive because Q square itself by itself is negative. Okay, that's why I use this capital Q square. So Q square is positive, P dot Q is positive, and this is the simplest expression that you can think of for deep inelastic scattering. And you can ask experimentalists actually to perform this experiment, look at the angular distributions and extract this for various values of incoming proton momentum of the incoming proton, and from the this looking at the momenta of the final state leptons, you can find out what is the Q dependency. So for every possible Q and P, you can actually extract this as a function of P dot Q and Q square. These are two invariants. Okay, that's one task. Okay, now let us have a break and see what theories could tell about these things actually, because when this was going on, this people Bjorken, Gallman or Callan and people like that, they actually did not want to use any of these things. They just wanted to study this by looking at certain limits actually. Okay, is always practice. You just see if you have an expression, you study what happens at large Q square, large proton momentum, large photon momentum, and things like that. So we wanted to look at how this function behaves, because you have a an integral representation for this W mu. Okay, that is something that any this would look like. Okay, so I'll just write down what was one of those important findings while this was being studied experimentally. Okay, what was that actually? So this was actually by many people. I don't want to name only one of them, and the one who actually sort of made a very strong observation was Bjorken. Bjorken, of course, every one of you know, because nobody would miss to read this book, Bjorken-Trell. Okay, so Bjorken was the one who actually made a very important observation on this W1 and W2. Okay, by carefully looking at this W mu in certain kinematic setup. What is the kinematic setup that he looked at it, where he found very interesting thing happening actually? That's the question. So what he did, he studied this W mu using just this function, integral of this commutator of two electromagnetic currents in certain limits. What is that limit? Now we call it as a Bjorken limit. So I will also call this as Bjorken limit. What is that limit? The limit that he considered was that take Q square going to infinity. This what it means. Q square is actually invariant energy, whatever energy, invariant, the energy that is transferred is Q square that I have written down here. It's very large. Infinity means it just means large. Okay, so and P dot Q goes to infinity, very large. P dot Q, again you can see that P is actually capital M if you work in the center of mass frame, M into E minus E prime. If you really want to see explicitly, it is the energy that is transferred to the proton system multiplied by mass. Mass is just not an important quantity, this is just energy. So not only Q square is large, okay, which is this. So Q square large means you can see the angular dependency on this. Okay, so you'll have to look at very special events where these two conditions are satisfied. Okay, and not only this, I assumed that the ratio of these two quantities, namely, if I define this as xbj fixed, meaning I don't want to independently take the limits q square and p dot q to very large values, but I take it in such a way that the ratio is always constant. Okay, this is the very special limit that I considered, where you could do lot of manipulation on these expressions just using simple, mathematics. It's a Fourier transformation of some product of some very nice looking functions which has nice properties. Okay, you could do some manipulations, and what he found was actually two things. One, if you take this limit q square infinity, p dot q goes to infinity, this xbj is finite, he found m times w1 q square comma p dot q is simply another function which depended only on this. He didn't put xbj, he had only x. Okay, and in the same limit, okay, limit let me call bj. Okay, this entire set I call bj. In the same limit, if you calculate this quantity p dot q by m, w2 q square p dot q is f2 q square by 2 p dot q, which is f2 of xbj. Okay, this is a remarkable, achievement in my opinion, because this really changed this flow of this progress, that how people actually studied this deep inelastic scattering. One is experimental, the other one is actually this. This is remarkable because in certain limit, I don't know why he chose this limit. You will see that actually this limit actually corresponds to say, situations in experimental setup where you create system in a very particular state. Okay, you will see that slowly. Probably add that in mind, and in that limit you can see that actually they are not independently dependent on this q square and p square, but they depend only on the ratio xpj. Okay, it's in some sense what people call scaling. Okay, it doesn't depend p and q separately, but it depends only on the ratio. So it's a single variable dependent actually. Okay.
To come to this point, you really need a tensor decomposition maybe.
You don't need to do, you have to look at, you need, of course, this tensor decomposition is fine actually. Okay, without that you cannot do it actually, but you can also study w mu as such, how it behaves, and then try to find out in certain limit that function behaves in a particular way, and you can find out certain combinations of w's multiplying m here, p dot q by m. You could show that it only depends on, yes, I mean this is necessary. It's not, this is not an independent step actually, because all are related. Okay. Okay, so this is remarkable. I will show you why it is remarkable, slowly. If I really substitute this observation in my formula and see, you get a completely different perspective. So I'll also, if you want, I can write down what this f1 and f2 in terms of those currents actually. Okay, it's not difficult to see. Okay, maybe I don't have space here. So I will write down. It is not going to shed much light actually, but unless you work out yourself. Okay, so I'll write down at least one of them. F1 of xbj. It's just minus I by pi limit pz going to infinity 0 to infinity d tau sine of xbj times tau times integral d cube x psi pz jx of x vector tau by p0 jx of 0 commuted to pz. So this is, by doing, doing manipulations in certain limits, you could show that actually the entire integral actually reduces to a simple looking form, from which you can deduce that it's not a function of two invariants, but it's only ratio to these two invariants actually. Similarly, you can write down f2. So you did not calculate anything, you just simplified the expressions in certain limits and showed that actually result which is only function of x bj, nothing else. Okay, so that's in the literature called a Bjorken limit, and the scaling is called Bjorken scaling. Okay, this is called Bjorken scaling. Okay, this is, in my opinion, is one of the first time that people had actually sort of realized scaling in physics. Okay, in deep inelastic scattering experiments, actually through deep inelastic scattering experiments. Okay, there are many other cases, but this is one place where you can really see there is something nice thing happening, which is not there in any other areas of physics, like electrodynamics and things like that. Now, what is this scaling in terms of understanding this? It's just some observations. So what? Yeah, I'll finish. What time I started actually? 9:45. So 1.5 hours.
1 hour 15 minutes.
1 hour 15 minutes. Okay. So there are people after me. So let me just complete that. Then you'll get some feeling. In 5 minutes, I'll try to finish. Okay. So let me just see in this context. Okay. If I just substitute that expression here, okay, the observation of Bjorken in the cross section, and see what it implies actually. All I need to do is actually I should look at this cross section in the Bjorken limit, which corresponds to replacing W1 and W2 by F1 and F2. That is all. Okay, that's one thing theoretically. And experimentally, what was that actually? So experimentalists, when they saw this, there is a scaling, they wanted to really verify that this is really happening or not, because this is just mathematical steps. Nothing, no physics is actually put in, except it's electromagnetic current that comes from physics observations, and rest of the things nothing actually. It's all mathematical. Okay, and then people did this experiment at SLAC. In 70s, and took this limit when they performed this experiment, keeping xpj fixed, and tried to see whether your W1 and W2, or this F1 and F2, extracted from this this formula from the data. Okay, they could actually see that they neither depend on p dot q nor q square, but the functions depended only on xpj. That was the great I would say success of what Bjorken did actually. What Bjorken showed theoretically using that simple looking formula, and SLAC experiment actually verified this Bjorken scaling. It could, neither Bjorken nor that experiment could get Nobel Prize. But that was in principle a starting point for writing down a theory, theory of strong interaction, namely QCD, which inherently enjoys this scaling. Okay, so without scaling, you cannot think of writing down a theory which should have this property. I'll demonstrate this. That's one thing. Two. Since I don't have time, Vaibhav is after me. So if I substitute, I'll show you by substituting this Bjorken, this Bjorken's observation into the formula, and I demonstrate that in the Bjorken limit, the scattering can be viewed not as electron scattering on a proton and giving X. I'll show you the electron scattering on a bunch of free, bunch of states which are weakly interacting. I will show mathematically how that picture emerges. That picture goes by the name Parton model. Okay, that you can view this process in certain kinematic conditions, namely this Bjorken limit, as scattering or incoherent scattering of lepton on point like weakly interacting particles actually. So this picture emerges very beautifully thanks to this observation actually. Okay, we will show when such picture emerges and how Bjorken thought about this limit where the proton would look like it takes that particular state where you can replace proton by a bunch of point like weakly interacting particles actually. Okay, that picture emerges simply because of this very great observation actually, I would say. This was one of the breakthroughs in my opinion in strong interaction physics, the first breakthrough, and that led to what is called Parton model, which I said the picture of proton in this particular kinematic situations. Number two, the scaling, and the scaling was an hint to look for case theory that can actually enjoy this scaling property. Okay, QCD of course in large energies, particularly in Bjorken limit, if you take, you will find that the coupling constant vanishes, it's asymptotically free and things like that. So you sort of converge to a case theory that was possible simply because of this. Okay, so in the next class I will show you how one Parton model can be realized from this observation, and I will also proceed and show that mathematically how you can write down a Parton model. Mathematically, you can write it as cross section in terms of Parton level cross section, which people call factorization. Okay, long distance physics, short distance physics, and things like that. What they call factorization. That will be my next talk actually. So I will continue with this.